All right. So we're going to continue with chapter 1, speaking mathematically. This section is on the language of sets. All right. So the use of the word set was, as a mathematical term, was introduced by, I guess it's Georg Cantor. But basically, for most purposes, you can think of it as intuitively. It's a group of elements. Formally, with the set roster notation, if S is a set, the notation X, that symbol S, means that X is an element of S. With a line through it, the notation means X is not an element of S. A set may be specified using the set roster notation by writing all of its elements between braces. You can use ellipsis to describe a very large set or an infinite set, as the examples give. You might recognize that notation as being how to define an array in C++ to when you want to specify the elements of the array. An array is a type of set. It's a particular type of set. This notation is used for sets in general, but an array is a type of set. The axiom of extension says that a set is completely determined by what its elements are. It doesn't matter what order they're in or if there's repeated elements. This is not like an array in C++. An array in C++ is ordered, and if there's a duplicate, there's a duplicate. An array with a duplicate is not the same as an array without a duplicate. So they are different in C++. But when speaking about sets in general, you can have duplicates and the order doesn't matter. So for example, if A is 1, 2, has the elements 1, 2, and 3, B has 3, 1, and 2, and C has 1, 1, 2, 3, 3, 3, they can be considered equivalent sets. In C++ or programming in general, an array that has these different orders and duplicates would be different arrays. An important thing to remember is B is the set with the element 0 equal to 0. No, it is not. The number 0 is just a number. A set with the element of 0 is a set. It's a different item. Like in C++, a number 0 is an integer, whereas an array with a single element with the value 0 in it is a distinctly different object. One's an array, one's an integer in C++. With B, the first in the curly braces, that's a set with an element of 0. Whereas the number 0 is just a number. How many elements are in the set 1 and another set of 1 in it? There are 2 elements. The number 1 and another set with the element 1 in it. This is kind of like a two-dimensional array in C++. I don't know if you've gotten into that sort of thing yet, but a set can have sets as elements. This would be, like I said, similar in nature to a two-dimensional array in C++. You have the wide curly braces defining the main set, and then you have curly braces inside that as elements of the array, so giving it a two-dimensional quality about it. As a little exercise, for each non-negative integer n, let u sub n equal the set n comma minus n. What is u1, u2, and u0? We already went over this. The A, B, and C have the exact same three elements, 1, 2, and 3. Different ways of representing the same set. And B covered that as well. And look at D. 1 comma minus 1. N and negative n and negative n. 1 and minus 1. U sub 2 would be 2 and minus 2. U0 is 0 and minus 0, which is equal to 0 and 0, which is equal to just plain a set with the single element 0 in it. So duplicates can be eliminated, and calculations can be used to simplify elements, like the negative 0 to 0. It's the same thing. So they are identical sets. Now, certain sets of numbers are commonly used, and they have special symbols for them. Capital R being the set of all real numbers, capital Z being the set of all integers, and Q being the all rational numbers. Remember the Q as being the quotient of two integers, is the set of all rational numbers. The addition of a subscript or superscript, plus or minus, or the letters non-neg, indicate that only positive, negative, or non-negative elements of the set are to be included. Thus, R plus denotes positive real numbers. Z non-neg refers to non-negative integers, 0, 1, 2, 3, 4, and so forth. Some people consider, some authors will use the set label N for natural numbers, being the 0, 1, 2, 3, 4, and so forth. So that can be seen, it can be run into as well with the capital N. You know what real numbers are. It's a set of all points on a line. 0 is in the middle, called the origin. Measure the distance. To the right, it's positive. To the left, it's negative. That sort of thing. Don't use number lines a whole lot. I think you basically stop using number lines in about 6th or 7th grade, something like that. But they use it as just to represent that it's all points. So all real numbers form a line. Set builder notation. Let S denote a set and P be a property. P of X is a property that elements of S may have or may not have, or may not satisfy. We define the new set to be the set of all elements X such that P of X is true. And that's how it would be written. Curly brace, X, element symbol, S, bar, and then the condition, in which case, which the elements of the set satisfy. So, given that R denotes all real numbers, Z the set of all integers, and Z plus the set of all positive integers, describe the following sets. Those are the conditions that you would want to satisfy. So in A, it would be all points on the number line between but not including -2 and 5. For B, it would be the integers between but not including -2 and 5. So it would be -1, 0, 1, 2, 3, 4. And if you're just looking at positive integers, as in C, you would only include 1, 2, 3, and 4 in the set. So this is how that you would represent them. The number line with the open circle on the -2 and 5 to represent all points between but not including the endpoints. This is the notation for B would be the curly brace, -1, comma 0, comma 1, comma 2, comma 3, 4, comma 4. And then Z plus 1, 2, 3, 4. Pretty simple stuff. It's just it's a matter of just learning the symbols. Like I said yesterday or Tuesday, this is just formalizing common sense. You know what's intuitively or from previous classes, previous education. Subsets. A basic relation between sets is that of a subset. If A and B are sets, A is called a subset of B, written with that symbol, if and only if every element of A is also an element of B. Symbolically, for every that means A is a subset of B means that for every element of for every element X, if X is an element of A, then X is an element of B. The phrases is contained in and or contains are also alternate ways of saying that A is a subset of B. So that's the formal definition of a subset. So just kind of try to remember these symbols. It follows from the definition of a subset that for a set A not to be a subset of B means that there's at least one element of A that is not an element of B. So symbolically, there it is. Does anybody know what those symbols are, other than how they're read? Is there a name for those symbols? Subset and element, or not element of? It just occurred to me to wonder about that. But anyway, if for A and B as sets, A is a proper subset of B if and only if every element of A is in B, but there is at least one element of B that is not in A. A proper subset. And if I'm not mistaken, they don't. The first symbol is for a proper subset. The second symbol is for a regular subset. Subset means, a proper subset means it's this element, this set is a proper subset of B, whereas this, the first element could be equal to the second element. Hence, like the line underneath, kind of like the less than or equal. This is a subset, proper subset, or equal. So that's what the slight difference in symbols there is. They don't mention this symbol in the book that I'm aware of. At least not that I've seen yet. But a proper subset of B cannot be equal to B. So, some examples. A is positive integers. B is integers between and including 0 and 100. And C is 100, 200, 300, 400, 500. Is B a subset of A? Is B a subset of A? Why not?
Yes, asking. The question looks like that's less than 100 and 0.
It's B is all elements from 0 to 100 inclusive. So it includes 0 and 100.
And A is just asking for the positive.
And A is just positive integers. So is B a subset of A?
No.
Why not? It's not, but why not? B includes 0, which is not a positive integer. So B is not a subset of A. C is a proper subset of A. Is that true?
Yes.
Yes, it is. It is a proper subset of A because C is all. They're all positive integers, but there's an element of A, say 2, that's not in C. Therefore, C is a proper subset of A. C and B have at least one common element. Yeah, 100. C is a subset of B.
No.
No, because because B only goes up to 100 and C contains 200, 300, and so forth. C is a subset of C. It's a subset, not a proper subset, a subset. So it could be a proper subset or equal. So yes, C is equal to itself. So C is a subset of itself. So we went through this, went through each of these. In general, the definition of subset implies that all sets are subsets of themselves. So, yeah. Okay. Which of the following are true statements? 2 is an element of the set of 1, 2, and 3. True. 2 is one of the elements of that set. The set 2 with the element of 2 is an element of the set 1, 2, and 3. No. Because the second set does not contain a set within it as an element, which would then make it true. Oh, did I? 2 is a subset of 1, 2, 3. No, because it's not a set. 2 is not a set. It's just a number. A subset has to be a set.
Okay, so it's really about the sign.
It has to do with the symbols, yeah.
So A is correct because 2 is
Yes, 2 is an element. 2 is an element, but not, the number 2 is not a subset. Subtle difference there. The set with the element of 2 in it is a subset of 1, 2, 3. The set of 1, 2, 3.
what are we on?
D.
I don't think that's correct.
Subset. So is it a set? Is the first element a set?
Yeah.
Yes. So it is a subset of.
But it has the brackets.
Yeah, that indicates that the brackets around the 2 indicate that that is a set.
I'm thinking it's its own set.
It has a set. It is its own set, but it is a subset of the second set.
Okay.
Let's see here. The subset, or the E, the set with the single element 2, is it a subset of the set with, it's an element, not a subset. The set of just 2 is contained within the second set.
If there was just 2 with no curly brackets on it, then would it be a subset?
No.
What needs to pay for curly brackets?
It would need 2 pairs of curly brackets for that for the first term to be a subset of the second set. Now, I had said this just a few seconds ago. The element, a set with a single element 2, is an element of this second set. The set of set 1 containing 1 and a set containing 2, because the curly braces with the 2 containing the 2 is within the set on the right. So A, D, and F, yeah. Yeah. So, and we went through why they're true and false. Okay, Cartesian products. Okay, combining two sets. Given elements A and B, the symbol A comma B in parentheses denotes an ordered pair consisting of A and B together with a specification that A is the first element of the pair and B is the second element. Two ordered pairs, A comma B and C comma D, are equal if and only if A equals C and B equals D. This is more like an array in C++. C++, the elements of an array are ordered. These are talking about pairs, but the principle still is the same. The order matters. So, is 1 comma 2 equal to 2 comma 1? No, because the order matters. What about 3 comma 5 over 10 equals square root of 9 comma 1/2? Yeah, because if you simplify the terms, the elements are equal. What is the first element of 1 comma 1? Kind of a gimme. It's just 1, and the second element is also 1. Let's see here. Yes, by definition of equality of ordered pairs, 3 equals square root of 9, and 5/10 equals 1/2. And the first and second elements are both 1 in C. Now, the notation for an ordered n-tuple generalizes the notation for an ordered pair to a set with any finite number of elements. It takes both order and multiplicity into account. This is more like an array in C++. Order and multiplicity of elements are a factor in the makeup of an array. So if x1, x2, x3, so forth to xn equals y2, y1, y2, y3 to yn, this implies that x1 equals y1, x2 equals y2, and so forth, xn equals yn. So if you're like comparing an array in C++, you would start at index 0 and compare index zeros between two arrays to see if they are equal, and loop through and compare each element to its corresponding indexed element in the second array. So, is 1, 2, 3, 4 equal to 1, 2, 4, 3? No. Is 3 minus 2 squared 1/2 equal to the square root of 9, 4, and 3/6? Yes, because you simplify the terms. So, let's see here. Now, Cartesian products. Okay, given a set A1, given sets A1, A2 to AN, the Cartesian product of A1, A2, A3, so forth, is denoted with the X symbol, the A1, X, A2, X, A3, so forth to AN. It is the set of all ordered n tuples, A1, A2, A3 to AN, where A1 is an element of little a1 is an element of set A1, A2 is an element of the set A2, and so on. So you get ordered pairs of every combination of or ordered tuples of every combination of elements of all the sets. So if you're just doing a Cartesian product of two sets, A1 and A2, A1 is an element of set A1, and A2 is the element of set A2. It's it's basically all combinations of the elements between the two or more sets. So A is X comma Y, B is 1 comma 2 comma 3, C is AB. A Cartesian product with B See how that's every combination of the elements of A and B? There's 3 elements of B. So the first element of A, X, has the ordered pairs X1, X2, and X3. And the second element of A is Y, so we have Y1, Y2, and Y3. And it's all in a set. So it's a set of ordered pairs, would be the answer. Yes, each element is, you pair up each combination of elements. So, jump down here, how many elements make up a cross product? Or not a cross product, that's a different math class. A Cartesian product. The number of elements in A times the number of elements in B. That's how many combinations there can be. So there would be 6 elements, because last time I checked, 2 times 3 is 6. I don't know, with this Common Core math, it may not be equal to 6 anymore. I don't know. But looking at B Cartesian product with A, you would have the B element first, so it would be 1 comma X, 1 comma Y, 2 comma X, 2 comma Y, and 3 comma X, and 3 comma Y, close, close. So the combinations get big quick, the number of combinations. Makes for a lot of writing or typing if you do it by hand. finding A times cross product with A, it would be XX, XY, YX, YY. And that would only contain 4 elements because two elements in both sets, 2 times 2 is 4. So now jump down to E, A cross product with B, quantity cross product with C. Notice the F is a very similar question. I'm not going to write those out. It's on the next slide, or pretty close to the next slide, and we'll look at those. And then let R denote the set of all real numbers. Describe RR. R cross product with R. I mean Cartesian product with R. No. All points on a Cartesian plane. Remember from geometry or pre-calculus, analytic geometry, whatever the class might be called. X and Y are real numbers. Combination of all real numbers. All combinations of all real numbers describes the Cartesian coordinate system. So, now let's look at E and F. Let's see here. That's E. The Cartesian product of A and B is a set, so it may be used as one of the sets making up another Cartesian product. In this case, for A, cross product or Cartesian product with B, quantity Cartesian product with C. So there's all the combinations. You do the Cartesian product of the A x B, and then use those as elements to do a Cartesian product with C. So going back to this, how many elements does E have? 12? 12, yeah? Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, yeah. Yeah, 12. 2 times 3 times 2. And then F, oh yeah. This is different because the Cartesian product is of 3 sets simultaneously, so it creates triples instead of ordered pairs. It creates ordered triples. All combinations of the possible of each elements of each set. So when you have parentheses, the associative property does not apply, the associative property in algebra does not apply to Cartesian products. Okay, so we went over the ordered pair of X and Y is a cross product, a Cartesian product. I need to get that out of my head. Of real numbers to real numbers. So in the typical graph, you use X and Y as an ordered pair. So if x is 2 and y is 4, it's a different point than 4 as x and y is 2. So order makes a difference in ordered pairs. And by extension, if you were to do R Cartesian product R, you would have all points in three-dimensional space. Ordered triple, X, Y, and Z. Another notation, important in both math and computer science, strings. A string is of length n over some finite set A. It is an ordered n tuple of elements of A written without parentheses or commas. The elements of A are called characters of the string. The null string is defined to be the string with no characters. I've never seen this, but they say it's often denoted with a lambda as lambda, but it is said to have a length of 0. If the set of A is equal to the element a set with the elements 0 and 1, then a string over A is called a bit string. So that's what computers deal with, is bit strings. Ones and zeros. It's all the computer understands. So let A be A and B. List all the strings of length of length 3 over A with at least 2 characters that are the same. So that would be AAB, ABA, BAA, AAA, BBA, so on and so forth. Let's see here. It says, in computer programming, it is important to distinguish among different kinds of data structures and to respect the notations that are used for them. Similarly, in mathematics, it is important to distinguish among, say, these 3 different notations because they are different objects. And you have to remember that on quizzes and tests and homework. We will be picky about the proper notation because different notations mean different things. I say we in grading. I have a TA that's going to help with grading the papers. So hopefully if you stick around after class, you may meet him. Some of you folks might already know him, but I'll introduce him he should be here around 2:50 or 3. So, all right, that's the end of that section. Let's see here. We've burned almost an hour, so let's see if we can squeeze in one more section. Got half an hour. See if we can move through this one pretty quick. Let me start the slideshow. All right. This one is the language of relations and functions. Okay. Let A and B be sets. A relation from R, which, why they use that, it's an italicized capital R as opposed to an unitalicized capital R, which is real numbers. So an italicized R means a relation. is a subset of the Cartesian product of A and B, given an ordered pair A X and Y in a product with B, is related to X is related to Y by R, written X R Y, if and only if X Y is in R. So R is a subset of the Cartesian, the Cartesian product of A, B, and B. Okay. A is called the domain. B is called the codomain. R with a slash through it means that they are not related. X and Y are not related by R. But some relationship exists. The set of R is a subset of the Cartesian product of A and B. So A and B, defined there, form a relationship that from A to B as follows. Given any X and Y as an element of the Cartesian product of A and B, XY is an element of R. It would mean that X minus Y divided by 2 is an integer. So, what ordered pairs in A Cartesian product with B, which are in R? Go through what there's 6 elements of the Cartesian product, because A has 2 and B has 3. So those are all the combinations. You have to go through each one to determine if the ordered pairs are an element of R. So 1, 1 is an element of R. 1, 2 is not. 1, 3 is. 2, 1 is not, because the equations don't yield integers, an integer. 2, 2 is an element of R. 2, 3 is not. So R equals 1, 1, the ordered pairs 1, 1, 1, 3, and 2, 2. The domain and codomain of R are basically just set A and B. So A is the first, the domain is the first set, and B, the second set, is the codomain. Here's where they get start using duplicate symbols again. Define a relation C where real number to real number as follows. Forget any given x, y is an element of the Cartesian product of two real numbers, such that C means that x squared plus y squared equals 1. So the domain and codomain of C are both real numbers. And draw a graph for C by plotting the points of C in the Cartesian plane. Anybody recognize that equation? Anybody? X squared plus y squared equals 1? Come on, go back to trigonometry. Don't remember? Yeah, it's a unit circle. It's a unit circle. A circle with a radius of 1 about the origin. So points on that circle would be elements of the C relation. And you got the unit circle as the graph. Now the arrow diagram of a relation is a way of representing a relation between two sets graphically. Typically, it works better with smaller sets, but you have one region with the points with the elements of A and one region with the elements of B. For each X in A and Y in B, draw an arrow from X to Y if X is related to Y by R. So let A equal 1, 2, and 3, and B equal 1, 3, and 5, and define S as and T as relations from A to B as S means that X is less than Y, and T is the ordered pair of 2, 1 and 2, 5. The arrow diagrams, you can see for S, 1 is less than 3, 1 is less than 5, so you have arrows going to them. 2 is less than 3, 2 is less than 5, arrows. 3 is less than 5, so it only has an arrow going to 5. And T is just the arrows from 2, 1, and to 2 to 5. A simple way to graphically represent relations between two sets. For those people that like visual learning better or think about things visually. Now, functions are a special type of relation. A function f from set A to B is a relation with a domain A and codomain B that satisfies the following two properties. For every element in A, there is an element y in B such that the ordered pair x, y is an element of F. And for all elements in A, or elements x in A, and y and z in B, if xy is an element of F and xz is an element of F, then y equals z. Okay, what that in simple terms means for every element in the domain, there is a corresponding element in the codomain. And no two, for each element in the first, in the domain, there's only one element in the codomain that matches it. So when you look at it properly, the square root of positive real numbers is not a function, because the square root of 4 can be either 2 or minus 2. it is not technically a function by this definition, because there's more than one answer to the condition, the relationship. That's why when properly, when doing computations involving square roots, you should specify explicitly whether you're referring to the positive square root or the negative square root of a number or variable, because the positive square root and the negative square root are both functions, but you need to distinguish between the two. In some instances. So let A equal 2, 4, 6, and B equal 1, 3, 5. Is R is that relation? B S is y equals x plus 1, and T is the function, is a relation defined by the arrow diagram. All right. Is R a function in A? I see heads shaking. No, it is not, because 4 from the domain has 2 corresponding elements from the codomain. How about S? That's a little bit more complicated. You need to write it out. We'll look at T, C. It's defined by the arrow diagram. Is that a function?
Yeah.
Yes, it is a function because there's only one arrow coming out of each element of A. All elements of A have a corresponding element in B, and no duplicate arrows coming out of elements in A. Not all the elements in B are referenced. That's fine. That doesn't matter. It just matters that all elements of A have a corresponding relation with an element in B. And if you think about the functions that you use in programming, a function, although in an older language, they made a distinction. If a routine returns a value, it's a function. If it doesn't return a value, it's a procedure. They did away with the term procedure in subsequent languages. But when you have a function in programming, you designate this. You typically designate the return type. But if not all code paths return a value, it throws an error. A function has to return a distinct value. That value could be a set. You could return an array, but it has to return a value. If a code path does not include a return statement, you'll get a compilation error. So, same type of situation. With the same inputs, you should get the same outputs from a given function. Okay, we went through that. S is not a function because it does not satisfy the property 1. It is not true that every element of A is the first element of an ordered pair in S. For example, 6 is an element of A, but there is no Y in B such that 6 plus 1 equals 7. Y equals 7. So you can also see this graphically by drawing the arrow diagram for S. See, 6 does not have an arrow coming out of it, so no dice. And we already looked at C. Let's see here. Let A equal the A and B. Let set be S be the set of all strings over A. The relation L from S to Z non-neg is as follows. For every string S in capital S, and for every non-negative number, non-negative integer n, S comma n is an element of L, means that the length of S is n. Observe that L is a function because every string S has one and only one length. Two strings can have the same length, that's fine, but you can only have one length of a string. Let's see here. Define the relation C to S, or C from S to S as follows. For all strings S and T in S, S comma T is an element of C, means that T equals AS. Basically, it means T is the string S with the A added onto the beginning of it. This is a concatenation function. So it is a function because every string S consists entirely of A's and B's, and adding an additional A on the left creates a new string, typo there, that also consists of A's and B's, and thus is also in S. So C, A, B, A, B, A, and B, B, B would be, the length would be 6 with the L, the length function, 6 and 3, and the resulting concatenation would be A, B, A, B, A, and A, B, B, B. Now you can look at functions as machines, black boxes. So you put an input in, you get an output out. What happens in the middle? You may or may not know. If you call functions from a library that you import in a program, you may not know how the processing works in the middle, but you know if it compiles, it will result in a definite output when you give it an input. The squaring function, f of x equals x squared. That's basic algebra. No matter what real number input is substituted for x, the output of f will be the square of that number. Every real number has a square. You can use the boxes type of thing we covered on Tuesday. Symbolically, f is x, right arrow, x squared. The successor function is from integer to integer is g of n equals n plus 1. No matter what you put in, you get n plus 1. So the constant function is where the result of a function is the same regardless. That's like calling a function that returns void in programming. It returns the same thing every time. They have these cute little diagrams with the function boxes and all that sort of thing. Let's see here. A function is an entity in its own right. It can be thought of as a relationship between sets or as an input-output machine that operates according to a certain rule. This is the reason why a function is generally denoted by a single symbol or a string of symbols such as f, g, log, or sine. These are all functions. A relationship is a subset of a Cartesian product, and a function is a special kind of relation. Specifically, f and g are functions from a set A to set B. Then, if f is defined here and g is defined there, f equals g if and only if for all outputs of x from f equals the outputs from g with the input of x. The functions would be the same. So, if the function f is the absolute value of x for all x that are real numbers, and g of x is the square root, more properly the positive square root of x squared, for every x is being a real number, does f equal g? Do they yield the same results? They do, because the absolute value of a real number equals the square root, the positive square root of its square. So there you go. That is it for this section. Hope I didn't go too fast on this relations and functions. But I will have the slides on Canvas this evening and the video tomorrow mid-morning, afternoon. The video should be on YouTube and the link in an announcement. We're going to finish up Chapter 1 on Monday. Thursday, we are going to have a quiz on Chapter 1. So our first quiz of the semester will be next Thursday before we start the lecture. We're not going to take the whole class on the quiz. So be prepared. Get your notes ready. Have a good day.